lavas of the Pacific Northwest. That's the topic tonight. We've got both a map and a cross-section of these great lavas, these flood basalts. So let's say you don't know anything about these. You probably do, but let's just say you don't. Is it true that these bedrock layers in eastern Washington are lava rock? They are. Is it true that those lava rocks, these flood basalts, came from Mount Rainier? They did not. When Mount Rainier or any cone-shaped volcano in the Cascade erupts, they make andesite lavas or rhyolite lavas or dacite lavas. These are different kinds of chemistries. And these are basalts. Look at this map. Look at how much of the Pacific Northwest has this thick pile of basalt lava. It's nothing to do with the Cascades. Let's get that out of our minds right now. Mount Rainier, Mount Hood, I don't care. Nothing to do with tonight's talk. Is it true that these giant lava flows, and they are giant, some of them traveled 300 miles, some of them are more than 100 feet thick. Is it true that those lava flows are unusual? Sure. I mean, they're bigger than the lava flows you see in Hawaii or Iceland, where we're going to go tonight, by the way. But is this the only place in the world that we have these kinds of lavas? No. No. There are flood lavas like these in Siberia. There are flood lavas like these in India. Well, okay, fine, but ours must be the biggest and the best, right? I mean, you know. No. We are small potatoes compared to these other flood basalt areas, and we will look at the volumes tonight as well. Have you heard this one? There's mass extinctions in our planet's history, where large percentages of all living things disappear from the fossil record. Mass extinctions. You've heard of those maybe? Have you ever heard that there's a connection between these flood lavas, the age of these flood lavas, and these mass extinctions? Oh, some of you have. Well, good. Well, I'll expand on that as well. So we got a lot to talk about in addition to the basic stuff I've always done. One more introductory comment. This is just a big pile of lava surrounded by stuff that's not lava, essentially. And in this cross-section, we can see this stuff here that's just buried beneath all this lava. So if you are a geologist who loves all this old rock, all these metamorphic and granite rocks, and they tell all these old stories of Washington, you hate the Columbia River basalt lavas. If you are a person who loves all these rocks or loves all these rocks, you're not a fan of these flood basalts, because the flood basalts have buried almost everything. Here's one place that the lavas have not buried everything. That's called Steptoe Butte over by Pullman. That's a mountain peak that kept its chin up above all of these lavas. But most of those mountains are still down there. They're just under, and I'm not making this up now, 2 miles of lava. In some places, more than 3 miles of lava. So I've heard on field trips geologists who love these other rocks talk to this as a big giant cow pie. They're not a fan of our flood lavas, our great lavas of tonight. But some of you came into town, you had a beautiful meal downtown, so you don't want to talk about cow pies, and I understand. So let's not call it a cow pie, let's call it a German chocolate cake. How about that? Okay? Brown, rock, brown. So this is the cake. These are the lavas. Somebody get that. And the age of these eruptions is very specific. 17 million years ago is when these lavas began erupting. 6 million years ago is when these lavas ended. 17 to 6. We got a pretty good answer about what happened 17 million years ago to start this eruption story. We have less of a satisfying answer to explain why the system stopped. But at least these eruptions are something you don't have to worry about. You know, most of these geology lectures are some sort of terror thing, you know. It's you know, an earthquake and the thing's going to come in a landslide. So this is all stuff tonight just safely tucked in the past, and there's no chance in the foreseeable future we'll have any of these eruptions. A couple final comments from these images before we erase them and move on to something else. As I mentioned, these are mostly metamorphic and granite rocks. However, there's also, at the upper part of these old rocks, thick sections of sedimentary rock. The Swak Formation. Some of you know about the Swak Formation. We've talked about that in association with the Liberty Goldfields. So there are thick sections, thousands of vertical feet of sedimentary rock beneath many of these places where our German chocolate cake is. And the oil people have been here. They've been drilling. They've been looking for oil and natural gas. They were here in the 2000s. They were here back in the 1980s. Shell, folks from Canada. And they're probably coming back because there's enough indications that beneath this German chocolate cake there are large pools, large reservoirs of oil and natural gas. Depends on who you talk to. But that drilling has helped us understand exactly how thick these lavas are. The top of the German chocolate cake, in places, there's a bunch of dots here. This is loess. This is wind-blown silt. It's kind of right here on this map. Loess is wind-blown silt. It's silt that blew in off the winds and got deposited. This is still a bit of a question mark, even today. Where ultimately is the origin of the Palouse hills? So that's what I'm talking about. So if you get towards Pomona, you know those rolling wheat fields and all that. That's a unique landscape. Those hills are made out of this kitchen flour. Ultimately, it's still difficult to prove where that stuff came from. Yes, the Ice Age floods came and eroded some and redeposited it, but I'm talking about ultimately where did that loess come from to begin with. It's been called the Palouse Problem for more than a century in geology circles. I don't know if you can read this from the back, but this says land sinks. How much weight are we talking about? If we're going to erupt 2 miles worth of German chocolate cake and plop it onto this landscape before 17 million years ago? The answer is a lot. It's going to weigh a lot. And we are sure that this portion of the Northwest has been physically depressed. We have crustally loaded this section of North America, Pacific Northwest, with these thick lavas. You know, we do this with ice sheets, but the ice eventually melts away and the crust rebounds. This is permanently displaced, permanently depressed, down warped. And elevation of what? The Tri-Cities is 500 feet above sea level or something like that. This is a landscape that was at sea level or higher. These are mountains that are now more than 10,000 feet below sea level. That's how much crustal loading or sinking we're talking about. So the mantle, which is below the Earth's crust, must have been displaced or flowed away from this subsided region. Okay, onward. Oh, you'd like, well, can't we do a little question and answer here? No, there's 250 people here. We can't do that. Okay, so we're moving on. We're keeping it going. So let's take that German chocolate cake, which again is our stack of lavas. By the way, there are 300 separate lavas. Did I say that already? Maybe, maybe not. Let's do a little stratigraphic column. Let's basically go through our cake from bottom to top. We're drilling down into these lavas now. And I'm not going to go through all the literature and all the names and all that sort of stuff. I've done that work for you. But down here at the bottom, here's 17 million years ago. Here's 6 million years up here. Now that's a misleading way to say this. Technically that's true. These lavas came out 17 to 6 million years ago. But as we'll see here, it's not the best way to portray what we're talking about. 15.6. We can really subdivide these eruptions of these basaltic lavas into sub-events. We have kind of an initial phase of the eruption. The first 1 million years are relatively minor lavas coming to the surface. There's a payoff for this discussion, by the way, coming in just a second. And then we have a main phase where the system is really working full throttle. And notice that's just 400,000 years, but that's, it's a relatively tight window where we're really pumping out these lavas, and these lavas are literally coming out of the ground in Idaho and flowing to the Oregon coast. It's just during that main phase time. And then this waning phase, these are not my words, these are from some of the geologists who've been working on this. The waning phase is more than 10 million years. There's minor little drips and drabs and little worms of little orange things coming out just on occasion. But this thing has finished with a whimper. It has not finished with a bang. We'll talk about some of these waning phase lavas because they are most prominent in Washington. The Ginkgo lava flow, the Rosa lava flow, maybe some of you know some of those names. But this point of this stratigraphic column is to show that we've got a main phase right here. Okay, with this map, hey, you want to see a magic trick? I got an eraser. I only got one eraser up here. You ready? Turns out Sharpie markers also have Sharpie markers with paint. It's like a paint can. So, okay. Why 17 million? And where are these lavas coming from precisely? There's a relationship with these lavas to the Yellowstone Hot Spot. With the Yellowstone Hot Spot. So let's fill you in. And there are some problems with this connection. Not every geologist loves this idea. But I'm a fan, and many people see at least a timing connection, and that's what we want to try to do. So, where are these lavas? The lavas are here. They came out of cracks. Sure. Where are the cracks? Well, let's go backwards. The waning phase cracks, as we'll see with these beautiful maps I have for you, are generally up here in southeastern Washington, the ones that are young. Let's go back in time. During the main phase, the cracks are here. During the initial phase, in other words, when this system got started, the cracks were down here in southeast Oregon. So we're not making a cake, and we're not having the lavas come up each and fill the same cake every time. There's portions of the cake we're building geographically at different times. Here's the point. This whole volcanism story to make this German chocolate cake is starting down here. And these cracks are getting younger as we go north. Something is happening initially here, and by the time we're done, the cracks are opening up here in Washington. That's the convincing evidence. All these cracks are not the same age. That's the convincing evidence that it's related to the Yellowstone Hot Spot. And you're like, what? Yellowstone? Is that like Wyoming? Yes. Yellowstone is right here. It's a big circular crater that went kaboom 640,000 years ago. And then if you go further back in time, there was another crater here, and another crater here, and here, and here, and here, and here. There's a whole beautiful string of pearls that stretches across much of this map. Each of these is a circular caldera. Each is from an explosive volcanic activity related to the Yellowstone Hot Spot. The concept is, today there's a Yellowstone hot spot beneath northwestern Wyoming. But in the past, the Yellowstone hot spot was at different locations. 5 million years ago, the hot spot was at Pocatello, Idaho. 10 million years, it was at Twin Falls, Idaho. 17 million years ago, where was the Yellowstone hot spot? Right here in northern Nevada, where we have our earliest cracks forming at the same time. Is that a coincidence? You can't tell me it's a coincidence. You can't tell me the cracks that are making our lavas and this Yellowstone hotspot story happens to be at the same place at the same time without any connection whatsoever. By the way, last winter we had a lecture talking about evidence for the Yellowstone hotspot being 55 million years old at least. 55. And you go, well, the hot spot then is moving 55, 40, 30, 20, 10 here. Some of you know this. The hot spot is not moving. The North American plate is moving over the stationary hot spot. We can still get the same pattern, right? Instead of moving the heat source, we're holding the heat source steady and we're moving the North American plate over the top. Regardless, all I'm trying to say is that there are temporal and spatial connections between the Yellowstone hotspot story and these cracks. I'll give you one example of what's a problem with this. Why would the main phase be up here when we initiate the story down here? Wouldn't you expect the biggest and most voluminous lavas to come out where we have the heat? You get it? So there's a lot of back and forth. But Yellowstone hotspot is a story that I like. We're keeping it moving. We're keeping it moving. Where's my little sketch here? Hang on just a sec. Right. One more thing. So the whole cake was not built steadily, as I've already implied. 90% of the volume, 90% of the magma that came to the surface came out during that 400,000-year-old time. Only 7% of the Columbia River basalt flood province came out early, and only 3% of the total volume came out in the last 10 million years and change. If you're a numbers person and love the number of flows, we're talking roughly 180 separate basalt flows during the main time, 100 flows roughly in this waning time, and 20 flows initially. Hopefully my math adds up to 300. Okay? Good. I want to do a couple more things with these chalkboards, and then we've got to go to these places. I've got specific directions for you. That's maybe the thing I'm most excited about tonight. Specific driving directions on how to get to some of these cracks, how to know you're at ground zero for some of these eruptions. That's what we're going to do right now. Oh, there's murmuring in the crowd. You like that. All right. So here are the cracks. We know they're not all the same age, right? Now, I've been here 25 years, been teaching about these lavas for 25 years, so I have a standard approach that needs updating. That's why we're doing this lecture, you know. I'm kind of bored with it. It's kind of stale. So here's one thing that I had no idea about until 2 years ago. And I got so excited that I spent much of a summer out there playing around with this discovery. And I didn't make the discovery. I have people who help me find new scientific papers. John Lash or other folks send me good information, and I just follow those sorts of things. So for 25 years, I would say, hey, students at Central, you want to go find these cracks. These are called fissures. That's where the lava came up. If you want to go find a fissure, you've got to go find what we call a feeder dike. In geology, as a dike is typically a vertical wall of rock that cuts across Grand Canyon-like rocks. All right, so we got just horizontal layers. We don't care what kind of rock it is. And then cutting up through those horizontal layers is this vertical feeder dike. And this is basalt, right? That's the kind of rock we're talking about. If you don't have a visual basalt, you'll be sick of basalt by the time we're done with all the photos, etc. So again, up until recently, I would say, well, there's a dike here, there's a feeder dike here, there's a feeder dike here, there's a feeder dike here. In other words, there's these places where you have deep river canyons, you've cut into the earth naturally, and you look at the walls of the river canyons, you can find some of the plumbing system, basically, of these fissures that erupted material. And that is true. I'll show you some of those, and I'll show you how to find some of those specifically. Here's the part that I got excited about. Are you aware, this is my attempt to draw in 3 dimensions, by the way. Are you aware that even though some of these eruptions were 15 million years ago, there are still places on the surface where you can see the lava after it came out of the sky and fell on the ground. In other words, when this lava is liquid and orange and Hawaiian-like, we have a fire fountain. We have gases coming up with the lava. It's throwing these globs of basaltic magma, just, you know, globs of butter, just falling out of the sky and landing right next to the vent. I didn't know that. I thought it was all just these old feeder dikes down below. But what I want to show you tonight, especially with a little video clip, is spatter. Finding places where there's actually, honest to God, spatter that's 15 million years old, that's right next to the road that you've driven. You drove by it, you didn't know. You're driving to Spokane on the freeway, and you're driving right over a big place where there was a curtain of fire, and there's spatter falling out of the sky. I didn't know it either. So it's not only this plumbing system of these vents, it's this material coming out of these curtains of fire. So we want to picture this like a fountain in a shopping mall, but it's not water, it's orange Hawaiian lava that's propelled hundreds of feet up in the sky and then having this stuff fall and come to rest. It's a nice visual. I got one, so each of these are not the same, in other words. We get old to young, and the young ones especially have some of their spatters still preserved, while the older ones can only be found with deep dissection. Okay, got one more thing with the chalkboard. Perfect. What else did I have in the introduction that we haven't expanded on? Yeah. Comparing our German chocolate cake with Siberia and India, and ultimately linking them somehow to mass extinctions in our fossil record. Let me do this quickly, see if this works for you. So let's pretend this is Geology 101 now, and it's the first day, and you're learning the geologic time scale. This is of our planet now. And we've got this. And we've got the Earth forming 4,600 million years ago, 4.6 billion. According to science, that's the age of the Earth. 0 million years is right now, this evening, at the Hellholm Center in Ellensburg, Washington. 66 million years ago, 251 million years ago, 541 million years ago. Those are benchmark dates in our past. Why? Because each of these major benchmark dates talks about a significant change in the fossil record. And I'm not a biologist. I know very little about paleontology. But I do know that the Precambrian and the Paleozoic and the Mesozoic and the Cenozoic eras are subdivided by those major time markers, those major benchmark dates. For instance, I don't care where you find a dinosaur bone. I don't care what continent you are on. If you find that dinosaur bone, I know you are pulling that bone out of a rock that's between 251 and 66 million years ago. That's the way this works. Dinosaurs are only found in this particular thing. In other words, 66 million years ago, as many of you know, dinosaurs removed themselves from the fossil record. There's not one dinosaur bone that's younger than 66 million years ago any place on Earth. So that's the mass extinction. It wasn't just the dinosaurs, it was large groups of plants and animals that disappeared suddenly. This has been a mystery for a long time. This is not a lecture on mass extinctions. I'm just going to make this connection to these flood basalts. By doing what? By doing this. Let's pick 16 million years ago. Those are us. That's the Columbia River basalts tonight. We know it's 17 to 6, but let's just pick one number, okay? For main phase, start 16 million years ago. Those are the Columbia River basalt lavas. 66 million years ago, we happened to have an incredible pile of flood basalts in India. Is it a coincidence they're at exactly the same time that all these dinosaurs and 75% of all genus disappear from the planet? 251 million years ago, another major change in our fossil record. Happens to be exactly the age of the flood basalts in Russia, in Siberia. There's another one of these at 201 million years ago, which happens to be the boundary between the Triassic and the Jurassic. You've heard of Jurassic Park. So there's another tremendous mass extinction 201 million years ago. So let's do that. Mass extinction, mass extinction. There's another mass extinction. There's only 5 major ones in our history, and 3 of them happen to be associated with these flood basalts. The flood basalts that are 201 million years ago flooded onto something called Pangaea, where all the continents of the world were together in one big hunk. And it just so happens that as Pangaea just started to break apart, these flood basalts were coming up. Is there a connection between the breakup of a supercontinent and flood basalts and a mass extinction at the same time? Apparently, there's something going on that we still have not totally figured out. So I'll put Pangaea here just to kind of remind you. Last thing I want to do with this is to compare our cake with the other cakes. We're a cupcake compared to the other German chocolate cakes. I promise I just thought of that. Okay, great. So this is difficult to do, but I found some numbers from a number of different sources, and the numbers change a little bit from source to source. So this is the best I can do for you. I tried to look up the number of acres buried by this lava. Of course, these are going to be big numbers, right? And in fact, we need to do millions of acres buried. That's how much we're talking about. So all of our Pacific Northwest flood basalts buried 45 million acres. That first map I had over there with all the area that was buried, that's 45 million acres, Washington, Oregon, Idaho, etc. India, 370 million acres. Siberia, 1.7 billion acres. The Pangaea flood basalts, 2.7 billion. Are we on par with the other flood basalt regions of the world? According to acres, no. Oh, but maybe volume. Maybe we still have a chance. Maybe it's volume. Maybe if we just talk about the volume, the material, the amount of material that came out of the cracks in total volume, in miles cubed. 50,000 cubic miles for our Columbia River basalt lavas. I don't have room to write all these numbers, but you're starting to get the idea. India has 2.5 times our volume of material coming out. Pangaea, 12 times our volume. Siberia, 20 times the volume of the Columbia River basalt lavas. So I went to a national geology meeting a couple of years ago in Baltimore, and I sat through talk after talk on mass extinctions and the connection to these lips, these large igneous provinces they're called. So this is a real thing. And if you're waiting for some sort of scenario now with here's exactly what happened, I don't have it. And science doesn't have it. All I am comfortable saying tonight is that timing-wise, we are linking these mass extinctions with major flood basalt activity around the world. And you'll see on the couple of diagrams I have for you, there's more than just these four. Great. So it's important now to add the visuals. Ideally, we'd all jump in vans right now and we'd go out and find all these places, right? That's the real way to do geology. But the best we can do, well, it's either hit or miss here. I think we're good. Thank you. Oh, yeah. Will that work? Okay. Great. Thank you. So we want to do as much as we can with these visuals here tonight, do the best we can to kind of visualize this through maps and photographs and video clips. So of course we are here, centrally located in the state. It's a great place to study geology. But we are not centrally located in these Columbia River basalt lavas. We're at the margin. And that's also convenient for us. So we can study the lavas, but we can also go not very far north and get out of these lavas pretty easily. So uniformitarianism in geology tells us if you want to understand the past, you need to study the present very carefully. So there are active basaltic eruptions on the island of Hawaii, of course, miniature versions even of us, right? Miniature versions of the cupcake, but we still have that material. So if we go to the big island of Hawaii, we've had an ongoing eruption, the summit of Kilauea, for more than 30 years now. And this is how fluid this basaltic lava is. This is a lake at the summit of Kilauea. And here's another place that we have beautiful, not viscous, the opposite of viscous, very runny, very low viscous. That's almost water, isn't it? But it's lava. And when this stuff finally runs out of heat, it turns black, it turns brown, and it becomes basalt. This is the stuff we're talking about tonight. And this was Ellensburg. This was Walla Walla. This was Lewiston, Idaho, back during this time that we were talking about. This is maybe more accurate. This is this fire fountaining I was talking about. This is what we want to visualize when the magma comes to that vent and actually gets to the surface. These are gases that are sending this magma up into the sky. This is not slow motion, by the way. This is in Iceland. We're in a helicopter. The camera's kind of shaky. But this is more along the lines of what we want to try to visualize for some of the individual vents for these individual eruptions. Okay, well, let's take a little tour just to impress upon you how vast this region is. Moses Coulee, 2 flows there, two 2 lava flows of the 300, right? 3 lava flows here where US 2 crosses Moses Coulee. Vantage, Washington, 6 or 7 of these lava flows. You get it? You only see a few of the layers at a time. You never see the whole cake. You never see the whole cake. Look at the scale here. We're looking north at Vantage. Here's the I-90 bridge. Here's a huge semi, and here's one lava flow and another one. We just have 2 flows in that picture. Up on Saddle Mountains looking west. The Gorge Amphitheater. Everybody's enjoying the music, looking at the stage. There's always a couple geologists in the crowd not looking at the stage. Here's a friend named Tom Tabbert who likes to fly and record his flights. He's over Banks Lake, and we're getting a sense of kind of the horizontal nature. These are just 2 or 3 of the main phase eruptions up in the upper Grand Coulee. Yakima River Canyon south of Ellensburg. Think of how varied these locations are except for geology. Wallula Gap and the Columbia River. Each of these layers has been carefully identified, carefully studied. We know exactly how each of those flows traveled. This is Swallow's Nest Rock at Lewiston, Idaho. The Grand Ronde River Canyon, the place I'm going to introduce you to tonight. Wonderful part of southeast Washington. Great, and when we get to the edge of these lavas, it's an abrupt change. Here's north of Ellensburg. Get to the edge of Table Mountain and Lions Rock. You're out of our lavas, you're out of the Cowpie, and you're into this rugged, much older Stewart Range. Go west of Yakima, get up onto those flanks. You leave the Columbia River basalts and you get up into the Cascades, which again we know has nothing to do with tonight's lavas. And even out here at the Oregon coast, even all the way out here, we have our lavas that came out of the ground in eastern Oregon, eastern Washington, and in some cases even western Idaho. These are chemically matched. These are not guesses. We can follow these flows from place to place and put the story together. There's a beautiful brand new book called Roadside Geology of Oregon by Marley Miller. I know you know the Roadside series, but those are the yellow covered ones that are 30 years old. She's redoing some of these, and she had an interesting morsel I didn't know. Number one, Seal Rock, if you know the Oregon coast, is the southernmost place on the Oregon coast where you have our lavas. But this blew my mind. According to her digging in scientific papers, the lavas, once they got to the ocean, didn't stop. They didn't just kiss the shore and stop. They picked up speed, dug into the sediment beneath the ocean, made another pool of underground magma, had new feeder dikes and new eruptions on the floor of the Pacific Ocean. So this is quite a story. This is quite a story. So I want to make sure it's clear that I'm a teacher. I don't do any of this research. My thing is taking all this science and packaging it in a way that it works for a large audience. So the guy that did most of this work is named Steve Rydell, and he came out with a beautiful volume of technical scientific papers in the 1980s, 1989. And again, he came up with an improved, kind of updated version of those science papers in 2014. This volume is kind of the inspiration for putting this talk together. There's a lot of great detail in there. And it's not just Steve, even though I'm going to mention his name a few more times. It's colleagues of his that have spent their whole careers, 40 plus years, on foot, hiking around and putting this science together. They did a beautiful job. Steve also lives in the Tri-Cities, and for a while he was writing newspaper columns in the Tri-City Heralds, and he compiled those in a little book called Big Black Boring Rock. And so if you're into kind of casual science reading, kind of newspaper column type stuff, you can find that on Amazon pretty easily. Big Black Boring Rock by Steve Rydell. So hopefully you're now looking at this map of the Northwest with a new set of eyes. Look at how flat it is out here. We know why it's flat. The crust got loaded, the lava's flooded. They're called flood basalts for a reason, man. The Columbia Basin is a low spot because of the weight of those lavas. And this is a nice cross-section to show all sorts of things, but tonight we're just looking at our thick pile. So how thick is thick? This is a new map. So this is the first of many of these brand new maps I want to share with you. This is a map of our German chocolate cake, but these are thicknesses. This is an isopac map. So the lavas are, in total, the cake is a half a mile thick on this line, a mile thick here, 2 miles thick here, and at about Sunnyside, halfway between Pasco and Yakima, more than 3 miles thick. Now, how in the world do we know that? It's the petroleum people. It's the oil and natural gas people doing all their drilling. They spent so much money to get through all that worthless basalt so that they could finally get down to the rocks that would have the resources. So these are some of the maps of their holes. They drilled at Rosa Dam in the Yakima Canyon. They drilled Saddle Mountains a few places. And the result of that drilling helped us understand that the yellow here are flood basalts. The depths of the flood basalts are different depths at different places. But the real excitement here is that there's different rocks at different holes at different locations. Some of them swamp sandstone. Some of them metamorphic rock of an exotic terrain that came in off of the ocean. So this gives us real data to try to picture that pre-17-million-year-old landscape. And these kinds of diagrams are trying to put that together. It's a lost world, essentially. It's a whole landscape with mountains and valleys and different kinds of rocks that dominated our scene for a long time and now is just imprisoned. It's under this German chocolate cake with no hope of getting out, if I have to personalize rocks. If we go deep enough, we can actually get to the old craton if we're far enough east, so we can get to an actual part of old North America that seems to make sense. Some of the lavas in the German chocolate cake have some sandstone in between them. They're called interbeds. The Vantage sandstone is the most famous. These are important because we get all of our water from these guys. If you drill in any place where we have these flood basalts, you're trying to get down to one of these interbeds to get water. So, thank you for the map. Jennifer Hackett made all these maps. She lives in the valley here. She's on the school board. She runs a little company called Menashtashmapping.com. Beautiful, beautiful maps. So here's Jennifer getting us over to a place where we actually have islands that are not covered by lava. What's an example of one of these islands? Steptoe Butte, thank you very much. Here it is. So a mountain north of Pullman, south of Spokane, that's made out of quartzite, that's Precambrian, super, super old, hundreds of millions of years old, surrounded by flood basalts that are capped with that wind-blown silt, that loess I was talking about. So here's we got sound too. Here's a guy named Christian Sturm who flies drones. And he's flying from the south to the north, and we're getting a sense of the vast expanse of the flood basalts in all directions surrounding this mountain. Think of how many mountains like that are underneath the lavas, a bunch of them. But we've just got a couple like Steptoe. So that was pretty loud, and I like the loud volume. If that bothered you, you're going to be really bothered now. So this is our friend Tom, who's a bit more of a daredevil, so he's going to zoom by Steptoe Butte as well, but this is going to be wilder music and wilder visuals. You ready? Put your seatbelt on. Steptoe Butte right there. All right, we get it. Good. So if we're on our side of the flood basalts, we don't have steptoes. Instead, we have kind of wrinkle ridges where the lavas have been squeezed and formed into ridges. If you drive to Yakima, you go over ridges. Those are our lavas, but the lavas have been folded like a linoleum, like a kitchen rug on linoleum. No idea. Okay, great. So let's go to this source. That's really the thing that I want to hit the most with you. And if you've got the RV idling out in the parking lot and you're ready to roll, I can get you to some places that are at ground zero for these eruptions. So these are what the maps look like in the literature. They're not particularly sexy. The colors are me just taking my little colored pencils and trying to figure out which crack goes with which lava flow. It was fun, but time-consuming, and I had a lot of help from a guy named Andy Miner put all these individual flows together. And that's the basis of these maps I'm about to show you. But my God, I can't send you out with a map like this. It's just hard to read, this is all geophysical stuff from below the ground. So we need maps that are a little bit more clear, and that's where Jennifer comes in. So here's our lavas. There are all of our feeder dikes together. So if I only have 5 minutes to give this lecture, I would just show that and say that's where the lavas came out. But we're better than that, right? We know not all those cracks formed at the same time. Generally, we know feeder dike down below, curtain of fire up above, spatter falling out of this frothing fountain. And again, the curtain is what we want to have in our mind. We're not light enough here to really see this well, but we've got some orange lava coming up, and we can see one of those initial phase eruptions where the lavas don't get very far. These are the Steens lavas and the Imnaha lavas. Let's skip this. We can't see it very well. Skip. Now, after each eruption, we have a lunar-like landscape. This is Hawaii with no plants and animals on this featureless plain. That's what we can picture almost every one of these eruptions of our lavas. We're pretty sure we have thousands of years, at minimum, thousands of years between eruptions. This is not, Monday here comes one, Tuesday here comes one. These fissures are making these lavas, and there's enough time to develop a whole ecosystem before the next lava comes. That's why we have petrified wood and other remnants of these older times. This is way before the woolly mammoths. This is way after the dinosaurs. It's tough to put this into perspective time-wise. Let's skip those. They're too dark. Iceland, this is the best I've got with modern videography to approximate our curtain of fire. Hell, this could be Walla Walla going up to Ephrata to make the Ginkgo lava flow. I'll show you a map in a second. You're driving, you got your Skittles, you're just gassed up, you got the kids fighting, and you're seeing this out the window. This was us. This isn't some distant place. This was us. But of course, today, this is Iceland. So, let's do this. Initial cracks, the initial phase, make some lavas just down in southeast Oregon. Cool them off. Still in the initial phase, make the Imnaha lavas. Cool them off. Now the main phase, right? Main phase. Get these guys to go all the way up to Spokane, up to Upper Grand Coulee, out to the Oregon coast. And then let's just keep rolling. We're in a vibe now. This is all waning phase. Totally, this is 3% of the cake. It's nothing. But these are flows that affect us. And if you come next week, we'll talk about why these orange lava flows in some cases are so skinny, why they're so worm-like, and then they're flat, and then they're worm-like again. You can maybe figure it out on your own if you remember what the title is for next week. Vents in Oregon sending lava to Yakima. And this last little guy, just a little blip coming up right at Tri-Cities. Good, so let's go to actual places where we can see some of those sources. Let's do this again. Yeah. And now, Grand Ronde, this is the main phase. How can we find those feeder dikes? Well, one way we can do it is to go to the Wallowa Mountains. Have you been? This is down by Joseph and Enterprise. That's one way to approach. The Wallowa Mountains in the Wallowa-Whitman National Forest is mostly light-colored rock. The mountain range is mostly granite and limestone, light-colored stuff. And it makes it easy then to find our feeder dikes, because our feeder dikes are brown, right? We can find those squirts of lava coming up through, and during the main phase we had that. This was all underground, of course, at the time, but we can find these feeder dikes. This is all Andy Miner helping me out. Feeder dike, just sticking out like a stegosaurus plate. We did a backcountry trip this summer in the mountains. I knew I was doing this lecture, so we were on the hunt for these feeder dikes, and they were pretty easy to find. There's thousands of these feeder dikes. Each of the dikes are not very big. You're like, well, geez, that thing is going to feed a lava flow that goes all the way to the coast? No, but if you have 100 of these feeder dikes all active at the same time, you can feed some pretty impressive lavas. So feeder dikes, there's one right here in the trees. We have video of a feeder dike. Yeah, okay. So there's a waterfall there because of the feeder dike making that vertical resistant ledge. So all through the Wallowas, a lot of the main phase feeder dikes. Well, let's say you don't want to hike or you can't hike anymore. My knees are shot too. How about we drive? We go to the Grand Ronde River Canyon. So here's one of the best tips I've got for you. Have you been on this road? I hadn't been here until last summer. You go to Clarkston. Don't cross over to Lewiston. Fine town, I'm sure. But stay in Clarkston on the Washington side. State route, Washington State Route 129. Asotin, Anatone, Field Spring State Park, and you're going to drop down to the Grand Ronde River Canyon. This is primo country, or prime location for some of these beautiful feeder dikes. Each of these is a feeder dike from the Snake River all through the Grand Ronde River Canyon. And here's what they look at this road. Putting this road in to get through this impressive German chocolate cake, layer after layer after layer. But once we get down to the river, and we stop for some ice cream, can you see that something different is right here? It's a vertical layer of lava cutting across everything else that's horizontal. We're right here on the map. Vertical, cutting across horizontal. These are the feeder dikes that I have known about for 20 years. But they're impressive, and they are resistant. They stick out compared to the other parts of the cliff. It almost looks like firewood out behind your cabin. It's all stacked up like that. So, Grand Ronde River Canyon, a beautiful spot. You can just hunt for these feeder dikes. They're all over the place if you have your eyes tuned for this sort of thing. Beautiful. The plumbing system of this fissure eruptions. There's another one there. There's another one there. We got it, right? So we're building to what? We're building to the spatter. We want to go now to these newly discovered, at least to us, places where we can find where the lava came to the surface and fell out of the sky. I'm ahead of myself. We're still feeder dikes. I'm getting impatient. I hope nobody from motor pool's here. You're not supposed to go off the pavement, but I guess I did. All right. Good. We got it. We got it. We got it. I'm itching now. I'm itching. Good. So we're now into the waning phase. This is the Ginkgo lava flow. 15.4 million years ago, a crack opens up running from Ephrata to Moses Lake to Walla Walla. That vent is there. The spatter is there. So if you drive I-90 right there at one of the Moses Lake exits, you're going right through the curtain of fire, 15.4 million years ago. And look at this lava staying molten until it gets to the mouth of the Columbia, and a branch of this gets to Yaquina Head, the Ginkgo lava flow coming out of this crack at Walla Walla, or even Ephrata, is getting to the Oregon coast at Newport, Oregon. Impressive. Impressive. This is one of my favorites. This is the Rosa lava flow. 15 million years ago. Tokyo. You know where Tokyo is? Yeah, Templin's Country Corners, a little gas station like out of the 50s kind of a thing. It's the first exit you have when you're heading east away from Ritzville. That's the place we want to cross, the Rosa vent, Winona, Anatone. So this is what we visualize when we go out there. We can do more than visualize. Okay, you got something handy? The Esker Ranch. This is public land. If you want to go find this spatter I'm about to show you, you can go there. It's a short hike. You can drive basically right to it. We're halfway between Ritzville and Steptoe, and you're like, I've never been out there. There are hardly any roads out there. And you're right. It's one of the most remote places in Washington that I know of that's not high Cascades, and it's a really impressive stretch. And why are we going to the Esker Ranch? We're going to find Rosa spatter, this stuff that came out of the air. And by now I've built this up so much that it better be good, otherwise you're going to be massively disappointed. I'm a big dude, you know, but look at this this is just one pile of spatter, this stuff these orange globs that fell out of the sky, and the vent is right next door. So I went out there this summer with a guy named Chris Smart who works at Central. He's very gifted with a camera and with editing. And this is the subject of one of these short videos that are now on television. So let's give you that short segment. But hey, what about that giant volcano? If it's not Rainier, where is it? Probably not where you'd expect. Less than 25 miles from Ritzville and the freeway, we've got our volcano. This is it. Not a mountain, a flat area in eastern Washington that has evidence of an eruption 15 million years ago. This is a fissure coming right through this area, a deep crack. I know you wanted a mountain, but we got something different. There's something in this picture that's unusual. It's very rare. That red stuff across the way, that's volcanic spatter. The fissure is right next door here. Magma coming out of the sky and falling right where I'm standing. So this is a close-up look at spatter. I mean, it's basalt, but it's like whipped butter. It's like pumice that's dark colored. You can imagine these globs of spatter just falling and then on the ground 15 million years ago. And here's the resting place of a bunch of these guys. There's tens of vertical feet of these globs that have just fallen. And they're still relatively fragile. I mean, you can pull that right out. Here's another piece of spatter right here. 15 million years ago. This is ground zero for the volcanic activity. Spatter, the star of the show of that little episode. These are 5-minute episodes that are showing on PBS in Yakima, and in April they'll be showing in Seattle. So if we go back to Hawaii, we got mini versions of what we were just talking about. Little miniature fissure eruptions with the spatter falling and these lava flows falling away from those. I got a few more and we're done. Let's continue to present day. That was the Rosa. We were just here at the spatter out at the Esker Ranch. There's debate to this day about how quickly we can get this lava covering this area. With that particular Rosa flow we were just looking at, Don Swanson, a very respected geologist who spent 50 years studying this, thinks you can get that Rosa flow in 7 days. In 1 week, you can get it as far as, let me just go back. He thinks it takes just 7 days to go from here to here, all the way to the Dalles, and then get that stuff solidified. It's tough to approximate this. So there's others that think it takes months. One guy thinks it takes maybe a dozen years or more. So we'll maybe never know, but there's maybe new attempts. The Rosa flow we were just looking at is also famous because it makes the beautiful columns of Frenchman Coulee. And you've seen rock climbers, if you've been to Frenchman Coulee, that's the same flow. That spatter we were just at, that was the vent. Here's the lava being nice and thick, and when it cools, it cracks and forms these beautiful columns. Not every one of these lava flows forms columns. And it's still a bit of a mystery as to why some of the 300 layers in the German chocolate cake have beautiful columns, others not so well. Plenty of others that just don't have columns at all. An upper colonnade, a lower colonnade, and an entablature, which is kind of a squirrely cracked zone in the middle. They're all cooling cracks. Priest Rapids flow actually buried a rhinoceros up in the Grand Coulee called the Blue Lake Rhino. That Priest Rapids lava flow made it to Portland, and if you've been to the Vista House up above the Columbia, that cliff is this lava flow. So the reason that that cliff is there is there was an old valley that was filled with our basalt lava of the Priest Rapids. This is the Umatilla flow coming into central Washington. This is the, Soton, I think. I'm starting to lose my concentration here a little bit. God, if I am, are you? A couple of these I really like. This is the Pomona lava flow. Some of you know the Pomona Tavern, maybe, which is just north of Selah. The Pomona cracks opened up over here by Orofino, Idaho. Skinny river of orange lava following the old Salmon River. I'm giving away some of the juice from next week. Then the lava spreads into a sheet flow, buries central Washington, finds the Columbia River Valley, funnels back down to it, and gets all the way to the Oregon coast. Amazing. That's the Pomona lava flow. And this guy's my favorite, the Elephant Mountain flow. A vent down here in northern Oregon. It gets into a river valley and it pools here. Why is the Elephant Mountain my favorite of all the flows? It's photogenic, man. The Elephant Mountain is a minor flow. It's not very thick. It didn't travel as far as the big boys, but it has the most gorgeous columns. And the flow is so thin that you can take people your age. Maybe some of you in the room were out with us. We were out here in April, and we were hiking, even though many of us can't hike very well anymore. And we climbed up to the top of the Elephant Mountain flow, going up through these columns and getting up to the top. It's an accessible, this is public land as well, near Othello, Washington. So here's folks up there presiding over these beautiful columns. And if you get up there and look at the tops of these columns, they are so perfectly formed, so beautifully cracked. That's all cooling crack stuff. That's really not the topic of tonight, but I thought I'd include it. Oh, people love this. There's lots of talking right now. Look at that. There's a crack. Good. Finishing, oh, you saw the hammer, right. And then this last little guy is the Ice Harbor Eruption. I know this isn't 6, but close enough. This little guy, the lava got hardly at all. Lewis and Clark came down the Snake and encountered a terrible rapids right here, and that rapids existed. Why? Because that feeder dike was sitting right in the Snake River. So even Lewis and Clark were introduced to these Columbia River lavas. I love this diagram because it shows the feeder dikes are not going up to the same horizon. And if you think about it, that makes sense, right? Here's an older feeder dike, here's an older feeder dike feeding an older lava. Now we crack it again, get a younger feeder dike. In other words, you've got to build the layers before you can crack them. So that makes sense if you think about it, at least it did for me, thinking about that recently. Occasionally you find some pillows, which are circular features found only at the bottom of some of these lavas. These pillows tell us that the lava went into a lake of some sort, went into some body of water of some sort. So there's some details preserved there. These are some of the best pillows I've ever seen at the base of the Priest Rapids flow in downtown Spokane. And this is just to the west of downtown. And I think these are amazing because they're kind of three-dimensional. It's not just a highway cut. Not every lava flow has the pillows at the base. But if you find a pillow zone and then you're extra lucky and you're extra stupid, you get in your vehicle, you drive on the freeway, you cross at Ryegrass, you're heading to Vantage, you pull quickly off to the shoulder, you know that there's some holes, you go crawl in the holes, and you find petrified logs. They're right there. I'm not recommending this. State Patrol people will not be happy with me saying that, but your zoom, every time you drive to Vantage on the freeway, look for those holes down to the south side of the highway. John Lasher gave me that tip originally. And if you crawl in there, you can see those old logs. And many of the logs that are now at Ginkgo Petrified Forest State Park in Vantage were pulled out of those holes or holes like them in central Washington. Finally, we make the tie. Remember, we did this early on. We make the tie to the Yellowstone Hot Spot. Watch this now. We're today in Yellowstone. Let's go back in time, back in time, back in time until that hot spot is in northern Nevada 17 million years ago. There are problems, but generally the timing of that hot spot being here makes sense for the hot spot story and also makes sense for our cracks propagating to the north. And just in case you haven't seen this, you've got a big plume head, a mantle plume head that's upwelling and presumably feeding all of this volcanic activity 17 to 15 million years ago. The Yellowstone story, in case you can't picture it, is this: a stationary Yellowstone hotspot, a drifting North American plate, and you have these incredible explosive calderas, the biggest explosions we've had on planet Earth, all right here. Liz, where are you going? All right. It's my wife taking off. She's had enough. This is North America. It looks like this thing's moving, isn't it? But it's not, remember. North America is moving. This is southern Idaho moving over the stationary hotspot. That's what we visualize since the hotspot was in the northwest feeding the basalts. I'd mentioned that these large volcanic regions where we have flood basalts are called large igneous provinces. There's a wonderful book by Richard Ernst. It's pretty technical, but these are just some photos. I'm too cheap to buy the book, so I just took some photos out of the book. Each of these black splotches is a basaltic region, a flood basalt region. Here's Siberia, here's India, here's the Pangea flood basalts that are now, of course, separated by the movement of the continents, but originally they were all together. There are flood basalts in Greenland. There are flood basalts in Siberia. Look at how much Siberia is under basaltic lava. That's the German chocolate cake in Russia. That's Siberia. It looks like Yakima Canyon, but it's the flood basalts of Siberia. India, look at how much of India is buried in flood basalt. Many, many more times the volume that we have here. Flood basalts in India. Look familiar to us, but on a much larger scale. And this is the best map I have for the flood basalts 201 million years ago when Pangea was together. And then remember, very quickly after this happens, we split the supercontinent up. And so that flood basalt region is now separated by thousands of miles of water of the Atlantic Ocean. That event is partially responsible for the Palisades along the Hudson River near New York City. Let's skip that, let's skip that, let's skip that, let's skip that. And just point out before we quit that we have a brand new building at Central Washington University, the geology department and the physics folks. We're very grateful to have that building. You are welcome to come up anytime. And you'd go, why would I come to a building? Well, we've got some display stuff there, but we also have a classroom, and my classroom is open to anybody for free. Anytime I'm teaching, you are welcome to sit in here with these college kids and learn some basic geology about Washington. Seriously, so please, if you haven't, contact me if you like and come join us up there. I want to thank you tonight for coming, and I'll leave you with this clip involving my favorite flow, the Elephant Mountain. Thanks, everybody.